Yes, well, thank you very much for the invitation to speak here. I hope you enjoyed the first 10 minutes of my talk already. Now I have the slides. Okay, so what I'm going to do, oh, let me start the clock. I'd like to talk about fixed points in 4D and 3D Flatland quantum field theories. Now, this is a stream of research which has developed over the past couple of years, together with a couple of my students, Andy Bond, Gustavo Medina, and Tom Steutner, and particularly also Charlie, who is going to report on some of that in the poster session. So let me see. Good. So fixed points. I probably don't have to preach to the converted. I mean, we all know what they mean. They relate to thermal or quantum phase transitions, continuous ones, often of the Landau-Ginzburg type, characterized by universality classes. Okay. Now, more recently, people have become interested in also conformal phase transitions or possibly topological ones. And new phenomena such as deconfinement, criticality, or emergence have become of interest. Now, there's also an important link of fixed points in quantum field theory to conformal field theories, which from the conformal field theory point of view is exploited from the other side. So there is a lot of benefit for cross-fertilization here. Now, 40 people like myself, perhaps, we have a soft spot for ultraviolet critical points because we understand that these are important for a fundamental definition of quantum field theory. So asymptotic freedom being the prime example here, but more recently, people have also realized that actually high energy fixed points could be interacting, and people tend to refer that as asymptotic safety. Now, in 4D, people also have an interest in infrared critical phenomena, maybe the most well-known, the so-called Banks-Sachs infrared fixed points, which in extensions of QCD can be found, and also weak strong dualities, which have been discovered in supersymmetric theories. Now, what I'm going to do today is I'm hoping to give you an overview of what is known about weakly coupled fixed points in general 4D quantum field theories. And after that, I will progress and discuss some results in strongly coupled 3D quantum field theories, in particular Gross-Neveu. So let's start with 4D. Now, when I say 4D, what I mean is the most general type of 4D theory you could reasonably write down, namely something which involves gauge fields, all sorts of gauge interactions. You can write down what you want, effectively. Coupled fermions, these may or may not be charged under the gauge groups. We have scalars, which may or may not be charged. We have Yukawa interactions between the fermions and the scalars, and we may have quartics. Now, what you don't see on this slide are mass terms or higher dimensional operators. The reason for that is that these guys are not going to play any significant role for the existence of fixed points or otherwise at weak coupling. So we can safely drop them here and focus the analysis on these classes of theories. So in the sense, the theory space which we'd like to scan consists of Yukawa, gauge, and quartic interactions, such as shown here. And what you might expect is, of course, we will see the free Gaussian fixed point, which evidently exists always. We may find partially interacting fixed points with non-zero gauge couplings, but zero Yukawas and zero quartics. Or we may find even more fully interacting ones where maybe all of these couplings are non-zero. So in a way, we can think of it in the form of this table where I show you the qualitatively different types of fixed points that could arise, where Y means these type of couplings are switched on at the fixed point and N refers to them being switched off. Okay. Okay, so you can see these are Banks-Sachs type fixed points or gauge Yukawa fixed point where everything is switched on. But a priori, you could have scalar fixed points, so no gauge interaction, no Yukawas, or you could get scalar Yukawa fixed points where only the gauge couplings are switched off, but fermions and gauge and scalars together maybe form a fixed point. Okay, so what's then the result? The result of analyzing at weak coupling these types of theories is as follows. So you see here two blobs, one called yes, the other one no. and they refer to exactly what it is. Meaning, when it says yes, it means these type of fixed points can arise at weak coupling, whereas when it says no, they can never arise. No way of ever getting them in a controlled way at weak coupling. So the funny thing perhaps here is, well, before coming to that, okay, so there's some work underneath it. So if you can't sleep at night, maybe this is the page for you to look into, okay? But otherwise, let me try to explain what these results are and where they come from. So a key first feature is to observe that non-abelian gauge interactions turn out to play a crucial role in all of this. So we see in all cases where fixed points can be found, non-abelian gauge interactions need to be present. Now, the other important piece of information is given down here where it says IR or UV. So this is telling you whether these fixed points can be infrared or ultraviolet. So we see that most of them, in fact, well, all of them can always perhaps arise as infrared fixed point, but only one type of these can arise as ultraviolet fixed point. And so the interesting thing here perhaps is to observe that this does require the existence of all gauge, fermion, and scalar degrees of freedom for this type of scenario to happen. Now there's the second part of the panel where it rigorously says no, okay? So for many people, this is probably not new or not surprising, at least, because we have clearly not ever found any purely scalar theory with a fixed point in 4D, and similarly for scalar Yukawa theories and similar. Okay, so what does that mean? And where is this coming from? So let me first plot the RG beta functions corresponding to the different types of fixed point we have just identified. And in a sense, there are 5 different cases. Okay, so either your quantum field theory is asymptotically free, such as in QCD, then we run out of it, get into a strongly coupled domain, the theory confirms, we have beautiful standard QCD. But your theory may also be infrared free, so think of a non-abelian version of QCD with too many flavors of fermions, asymptotic freedom is lost. Yes, 40 people would say this theory is not well defined fundamentally, and they're probably right, but at sufficiently high energy, we can still take that as an effective theory, where the theory then probably will confine you to the gauge interaction. So we would have, you know, scalars and fermions, which arise as confined particles. But if we then go to lower energies, the theory becomes more weakly coupled, and we would observe the phenomenon of emergence, because the non-abelian gauge field is then set free and it will dynamically emerge out of such trajectories. And then we have settings with the Banks-Sachs type or gauge Yukawa type fixed points. So these two guys here have been known for quite some time. The new kid on the block is the green curve, where at the Gaussian fixed point, things start out positively. And so ordinarily, we think that these type of theories cannot possibly be fundamental. But then actually they can bend over and develop a nice ultraviolet interacting fixed point down here. Okay, so if you want, you can print this out, because this is the raw material for any weakly interacting fixed point in 4 dimensions. You can just, like, the most general theories you can construct with fixed points will be linear combinations of these curves shown here. Okay, so let me try to show you a glimpse of where some of these results are coming from, okay? And I cannot possibly cover all of it, but I will give you a glimpse of maybe the most important features for now. So I will explain why the Banks-Sachs fixed point, which is an infrared fixed point, has no ultraviolet counterpart. And I will also explain to you why gauge Yukawa theories are the only animals in town which at weak coupling can generate an interacting ultraviolet fixed point. Okay, so let's have a look into that. First, Banks-Sachs. Banks-Sachs means we only have a gauge coupling. So this is the beta function in the perturbative loop expansion. Minus b is the one loop coefficient, c the two loop coefficient. So for this thing to have a weakly interacting fixed point, we need b over c to be a small number. So clearly we know that if b is positive, c is also positive, and genuinely b over c small can be achieved. So infrared gauge Banks-Sachs is safe. However, if we want this fixed point to be ultraviolet, we need b to be negative, so the beta function to start out positive. And therefore, we would need c, the two loop coefficient, to be negative. However, it turns out there does not exist single quantum field theory where that can be achieved. And the reason for this, if you really boil it down into equations, you realize that a necessary condition would be that the quadratic Casimir of, say, your scalars, which are charged under the gauge group, must be smaller than the quadratic Casimir of the gluons by a factor of 11. So you can then make a table and just walk yourself through all possible gauge symmetries and representations, and you see that there is a lower bound for this relation being 3/8. So therefore, what we would have needed is something down here, but that simply doesn't exist. So therefore, there exists not a single quantum field theory where a Banks-Sachs is UV at weak coupling. Okay. Now, this offers us already quite powerful no-go theorems when in 4D you would think about UV completions for your theory, namely, as long as you don't have Yukawa interactions, it cannot happen. Just with gauge interactions, it's impossible. So now you may ask, can more couplings help? Well, let's take more gauge couplings. Answer is no, they cannot help, because gauge fluctuations always contribute with a positive sign at two loop to the beta functions in these settings. So nothing. You cannot generate a fixed point. We need, remember, a negative term to compensate the beta function. Now, scalar self-interactions cannot help you either. They kick in very late at 3 and 4 loop order. Okay. And even if they were quantitatively big enough, the scalars themselves cannot make a fixed point. So impossible. The only option which then remains are Yukawas. So let's see why. Let's write down the very same thing, but now including Yukawas. And the new thing which happens with Yukawas in any 4D quantum field theory is that their leading contribution comes with a negative sign. This is absolutely hardwired. Now, this negative sign is crucial because the negative sign makes sure that the growth of gauge couplings is slowed down. And if we're lucky, the D term here can cancel out the gauge terms, the gauge field contribution. And in fact, by looking into the coupled system of gauge and Yukawa couplings, you can then identify a necessary condition for this to happen. Okay, so which here I've exemplarily written down in terms of, a generic loop coefficients. Yes, but if these conditions are fulfilled, then indeed we would be able to actually find ultraviolet fixed points, interacting ones. Okay. So now the lesson from this is that there is a window of opportunities in order to find these new types of fixed points, provided we allow for Yukawa interactions in our theory. Of course, this doesn't prove that these things exist. So in fact, you would have to sit down and make sure there exist concrete models which do realize this mechanism. Let me give you a template for that. So you can do it with SUN gauge theories and Dirac fermions. You can do it with SON gauge theories and Majorana, or symplectic with Majorana fermions. Doesn't matter. All three avenues work absolutely safely. You need a certain type of scalar sector, which in this case will be elementary mesons. Okay, but whenever that happens, you will be able to, you have a quantum field theory which develops quantum field theory which is not asymptotically free. So you see the Gaussian fixed point here has only ingoing RG trajectories. Kava goes to the infrared. The gauge is not asymptotically free, so goes in. Okay. So clearly the Gaussian cannot be the UV fixed point. But the theory develops an interacting fixed point close to the Gaussian, where perturbation theory is rigorously under control. And this fixed point now has outgoing trajectories, either into the strongly coupled domain, where then the theory will be confining or possibly conformal in the deep infrared, or towards the weakly coupled domain, where the theory then will become free in the deep infrared. Okay, so we've been looking in all sorts of models when we tried to find examples, and we pushed these studies even to very high loop order, well, very high, say in these examples 3, okay, and just to be sure that these results are safe. Now, 15 minutes maybe. Now is a good moment for a small commercial break, because when we are studying all these models, we realized that it is extraordinarily tedious if we wanted to extract the RG beta functions from general expressions by hand. This is how we did it in the beginning, but we got a little bit tired of that. And so my former student, Tom Steubner, volunteered because he said, well, you know, I think I can write a code which is doing that job for me. And so there's now a code available, we call it Arges, which allows us to extract, well, which is written in the Wolfram language, and which allows us to extract general expressions for perturbative beta functions. Now, the new feature, which was very important for us and which might be helpful for others as well, is that the code has a lot of new functionalities which previous codes weren't quite offering. So in particular, we can keep field representations and multiplicities of fields as entirely free parameters. Also, the code has a lot of further functionalities which help with simplifying more complex tensorial structures in your interactions. Okay, so if you're working with these type of equations, give it a go. Of course, it's for free. You can do with it what you want, but hopefully it's useful for others as well. Okay, so that was the brief commercial break. Now back to the type of quantum field theories we were discussing. Okay, so I was saying we do find these new types of quantum field theories in 4D, which now have interacting and rigorously controlled ultraviolet fixed points. And in fact, this is something which also works in the context of supersymmetry. Now, for many people, this came as a little surprise, because it was thought for a long while that this is something that cannot happen in supersymmetry. And it, truth to be told, supersymmetry offers an additional constraint. It turns out that for this to work in supersymmetry, you need at least 2 gauge sectors, which is plotted here. So I have one gauge sector, which I call alpha 2, another one, which I call alpha 1. You see that the Gaussian is a saddle. It's not asymptotically free in one direction, but only in the other. So this is clearly not the UV fixed point of this type of quantum field theory. But then the theory can still develop an interacting fixed point, which allows outgoing trajectories, which is the one relevant thing for an ultraviolet fixed point. Okay, so to sum things up, I've shown you a couple of examples where the table in the beginning came from. Okay, I haven't spoken a lot about the infrared fixed points, okay, say because those were known for some time. So as an overview or as a summary for what happens at weak coupling, the message to take home is that there are only 3 types of fixed points: either the Gaussian, all couplings vanish, or a Banks-Sachs, all Yukawas vanish, but some gauge couplings are non-zero, or the gauge-Yukawa fixed points, where all gauge couplings, well, some gauge couplings are non-zero and some Yukawa couplings are non-zero. It's only the first and the last which also can be ultraviolet fixed points. Now, what are the implications of this? First of all, say from a 4D particle physicist perspective, yes, we now learn that in order to achieve ultraviolet, complete, or fundamental, well-defined 4D quantum field theories, we always require non-abelian gauge interactions. Now, this is something which, at least for us, came unexpected. Okay, so we are used to asymptotic freedom, and we fully understand that for asymptotic freedom to arise, non-abelian gauge interactions are key. But now it turns out that for 4D quantum field theories to develop weakly interacting fixed points, these non-abelian gauge interactions are also key. And in particular, they are key for these fixed points to become asymptotically safe. So in that sense, non-abelian gauge asymptotic freedom and asymptotic safety are in a way two sides of one and the same medal. Now, okay, so 4D people who have a background in particle physics, of course, can now have some fun with these type of ideas and try, to be courageous and think of models beyond the standard model, which perhaps realize these type of fixed points in an extension of for models beyond TeV energy scale. Okay. Now, the second implication, well, I mentioned it already, perhaps, is in the context of statistical physics point of view. Okay. So if you think about classifying universality classes related to 4D critical phenomena, yes, at least at weak coupling, we know exactly what we need to look for. And in particular, at weak coupling, we now have very clearly identified that non-abelian gauge fields are a crucial part for this to happen. Now this, if you want, this can open a door for a systematic classification of weak critical points in 4D, maybe in a manner similar to what had been done in the past in lower dimensional statistical physics settings. Now, there's another interesting link, I think, with works going on from the point of view of conformal field theory. Now, there are very strong results which have been made in the literature, which pointed out that any quantum field theory which is under perturbative control in the deep UV or IR asymptotes to a conformal field theory. So from that point of view, it is rather clear that all the models with all the weakly coupled fixed points we have just discussed correspond rigorously to unitary conformal field theories. So what this is now teaching us is that any weakly interacting 4D conformal field theory in one way or another has non-abelian gauge fields within it. Now that's something which from a CFT point of view, it looks absolutely strange, because that's not how you would normally look at your setting. You look from the point of view of primary fields, and you look into your constraint equations which arise from that. So there's no natural way of thinking of these things in terms of non-abelian gauge theories, right? But the examples which we've uncovered very clearly show that when these things are weakly coupled, non-abelian gauge fields in a Lagrangian formulation are necessary for that. Okay, so this closes to some extent the 4D part of my talk. And we can now scratch our heads as to see how what I've been talking about might help us understand critical phenomena in 3D. So Peter gave a very nice introduction as to how results from perturbation theory can actually be downlifted to 3 dimensions. And actually Wilson showed us how to do that. So you start in 4D with a degenerate Gaussian fixed point, say in a scalar theory, you downlift it. The fixed point, the degeneracy is lifted because of the downlifting, and you get a free and an interacting fixed point, which then becomes this famous Wilson-Fisher fixed point, of course. Okay, you can do the same with the abelian-Higgs model. Then you have 2 couplings which you can downlift and to lift the degeneracy, and you get the beautiful results Peter was talking about. Okay, so this is certainly one powerful strategy, and the game you could play now is to say, well, why shouldn't I start in 4D with something which has a well-defined interacting fixed point already there, and then downlift it to see whether it can survive in lower dimensions. So that's one possible strategy, okay? Now, for the rest of my talk, I'm not going to go down that avenue, but what I'm rather interested in is some rigorous results which can be achieved strictly in 3D. And to begin with, I will start reminding everybody about a few things which you're probably all aware of, so you can lean back now for a few minutes, okay? Because I'm going to start with ON symmetric scalar theories and the Wilson-Fisher fixed point. So what's the story here? So the story is you write down your quantum field theory, maybe, you know, some scalar field which has a mass, has a quartic self-interaction, maybe it has a sextic interaction, okay? So by power counting, we know that the quartic interaction now has a positive mass dimension. The sextic interaction is dimensionless, so the theory is beautifully super renormalizable. No worries in the world, okay? We also know that the theory can technically simply be free in the UV, and then we can flow from a free UV fixed point in the ultraviolet all the way down to Wilson-Fisher infrared fixed point. So the angle from which I would now like to look at this theory is from the angle of large n. The reason for this is that in large n, we can, some of the results can be rather rigorous, and this is what I'm going to exploit a tiny bit later. So what I'll be using is functional RG methods, maybe in the formulation introduced by Wetterich some time back. So you've already seen this flow equation. Sabine has been talking about it and others. When I did my PhD back in 91, starting back in 91 with Christoph, of course, I got properly vaccinated in that methodology, okay, including upgrades to the ERG and then later FRG, okay. And so nowadays, this methodology is called functional RG. I will use that name from now on. Truth to be told, other versions of exact flows have also been put forward, for example, by Polchinski a couple of years earlier. Okay, I will comment on some of that in a minute. Good. So let me see where we are. So let's now take ON in 3D and remind ourselves what the physics of this theory looks like at large n. So what I've plotted here for you is the phase diagrams. So you see two axes, the quartic coupling and the sextic coupling. Remember, the sextic is canonically dimensionless. So you clearly see that the theory can have a Gaussian UV fixed point. You can flow out of it and end up in the Wilson-Fisher fixed point. Beautiful, absolutely no problems. Now, there's an interesting particularity at large n, which is that at large n, the sextic becomes exactly marginal, meaning there are no quantum corrections to it. So you can fix a value, whichever value you want, and it's not going to run. A little bit like n equal 4 SUSY, yes, but only for one coupling. So you end up with a line of fixed points. People tend to call it critical, yes, for whatever value you choose for tau. But this line is going to have an endpoint. This endpoint has received some attention quite some time back. It's known as the Bardeen-Moshe-Bender fixed point. It's a fixed point where the theory has a proper fixed point. So you would expect that this corresponds to conformal field theory, yet scale symmetry is spontaneously broken. And now for larger sextic couplings, the theory no longer has a well-defined global potential. Okay, so it's rather a segment and not a line. Good. Now, you can do the very same thing with the Polchinski equation. Okay, so remember the Wetterich equation uses an infrared cutoff. The Polchinski equation uses an ultraviolet cutoff. And back in the days, people were banging their heads at each other because arguing that one formalism is better than the other, and that there are profound differences whether you have a UV or IR cutoff. Okay, but in this example, we see very clearly that it simply doesn't matter. The only difference you find if you use the Polchinski formulation is the coordinates look a bit different because this is a different parameterization. Okay, but the universal physics is exactly the same. You have a Gaussian fixed point and you have a segment of a UV conformal window. Now, in the parlance of ultraviolet fixed points, you would consider all these starting points as maybe asymptotically safe, simply because in the UV, the theory is not free, but it has a non-trivial, say in this case, sextic interaction. Okay, so let me see how I'm doing with time. So 10 more minutes. Okay, I think that should be fine. So one small technical remark. In fact, there is Polchinski-Wetterich duality between these two formulations of the model, which is rather intriguing because it's well known that the Polchinski equation in the approximation relevant for this study is completely independent of the RG scheme, whereas the Wetterich equation isn't. And so a priori, you wouldn't expect that they are related in any way. Moreover, the one has a UV, the other an IR cutoff. So why should they at all be related or carry the same physics? Now, however, the duality can be made absolutely rigorous in the sense that, say, if you were to be plotting your cutoff propagator, so that's this dashed line is the full propagator, 1 over p squared, okay, the same here. And if I now decide I cut it somewhere to split UV and IR, okay, maybe along this red line, then this is an infrared cutoff from the point of view of the Wetterich equation. So the Wetterich equation would retain information related to the modes down here in red, whereas the Polchinski equation retains the information encoded in the blue bit. And the sum of the two exactly gives you back the full propagator. Okay, and it so turns out the only subtlety here is that you should be careful in how you do the cut, because not every cut is going to give you the duality between the two formulations. But if you place the cut carefully, such as here, you have a rigorous map from all features and of one formulation of the corresponding path integral to the other one. Exact duality of formulations. So we see that whether you use a UV cutoff to implement your physics or an IR cutoff to implement your physics doesn't make a difference here. Okay, so last thing, what I show you here is a kind of heat map, an overview of, so a minute ago I just showed you the result for the leading couplings, say the quartic and the sextic, but you might wonder, is this a solution which extends over all field space? And in fact, this is what is shown in the heat map here. So let me explain. Rho is something like field squared, and W prime is the first derivative of, say, your effective potential. Okay, so normally you rotate these plots by 90 degrees. Somehow I didn't manage, so you have to twist your head to read it the normal way with, yes, the upside x is now the field variable. Okay, and so I've highlighted the Wilson-Fisher fixed point solution for you, and also the range of solutions which correspond to the tricritical fixed points, which are all the lines starting from the gray BMB1 and all the lines in between down to the black one, which is the free theory. Okay, so there's a range of UV lines indicated by these colors down here, which are all well-defined solutions, whereas those on the inside or those on the negative W prime axis will be unphysical. Okay, so last thing, what's the physics of the model? The physics of the model is you have a conformal fixed point in the UV. I call it asymptotic safety. This fixed point is characterized by universal scaling dimensions. Those I've plotted here for you. If these are negative, they correspond to relevant couplings. So these here correspond to the mass term, the quartic interaction, the exactly marginal 5⁶ interactions, and all higher order interactions are irrelevant. Then you can start from that fixed point flow to another conformal fixed point in the infrared, which in this case is the Wilson-Fisher fixed point. The Wilson-Fisher fixed point has a lower critical dimensionality. There's only one coupling which is relevant, as we know, which is the coupling which characterizes the second order phase transition in that model. All the other eigenvalues come out negative. So this theory and they will be irrelevant operators in the sense of the RG. Okay, so now in the final 5 minutes, I'm going to turn to Gross-Neveu in 3D. Okay, so the name of the game now will be I'm interested in fermionic interactions, and I switch on 4 fermion interactions such as this one. Now, the model has been proposed many years back by Gross and Neveu because they were interested in how mass is being generated dynamically in a 2-dimensional quantum field theory, because this theory in 2 dimensions is asymptotically free. And also, it is chirally invariant in the sense that this transformation, which forbids an explicit mass term, leaves the 4 fermion interaction invariant. Okay? So now the question, of course, back then was, how is mass dynamically generated in these theories? Okay, but after that, people got interested in how this model behaves in maybe 3 dimensions, okay? Now here's the catch. Unlike the scalar theory we were talking about a minute ago, this fermionic theory, the coupling has an inverse mass dimension, 2 minus d, so -1 in 3 dimensions. So back in the days, people, people were thinking, well, so perhaps these type of theories don't make sense fundamentally because they are clearly perturbatively non-renormalizable. So it's rather courageous to actually have a look into these. Yet, Gavetzky, Kupiainen, and many others have subsequently rigorously established that these quantum field theories are totally well-defined 3-dimensional quantum field theories, which are non-perturbatively renormalizable. And the token which is doing the job is the existence of an interacting ultraviolet fixed point. So this is by now super established, okay? And many facets of this theory have been looked into, both within perturbation theory, large NF techniques, but also within the functional RG, and within, say, Gross-Neveu Yukawa versions of that theory, which consists in bosonizing psi bar psi in terms of an additional scalar field. So what I'm going to talk about in the remaining 3 minutes is relaxing chiral symmetry. So I refer to this as Gross-Neveu plus maybe. So the idea is, with Charlie, we decided to have a look into what the role of chiral symmetry really is. And we wanted, therefore, to begin with simply giving it up. So when we give it up, the first thing which happens is that we are allowed to write down a mass term, obvious, okay? But also, we would be allowed to write down maybe a 6 fermion interaction, such as this one. Now, when you write down the 6 fermion interactions in 3 dimensions, you will see that the canonical mass dimension is -3. Okay, and so maybe people would consider you as delusional if you come up with asking whether this type of theory could be well defined microscopically. Okay, but for the sake of an exercise, this is precisely what we did. So we use this theory, and we now crank the handle and use the functional RG technology to exactly solve this quantum field theory at infinite end. Okay, so this is how the equations look like. Maybe that's not so super interesting, but let me highlight the crucial features of this quantum field theory. So the first thing is, so with this slide, I think I only prove that I cannot stick to my own conventions from one slide to the other, because now I call the mass lambda1, the 4 fermion interaction I call lambda2, and the 6 fermion interaction I call lambda3. But the important thing to notice here is that the beta functions you get out for the mass, okay, has an exact 0 if the mass vanishes. So mass equals 0 happens to be a rigorous hard fixed point of your theory. So if you play this game from the point of view of the generation of mass, you now have 2 options. You can say, well, I don't care, I can switch on microscopically mass and it will just be generated, fine. But you can also say, I switch it off, and then the quantum fluctuations in this quantum field theory have no way of ever switching it on. It will remain switched off. So that's the first point of information. Now, you may ask, what is this meaning? What is this implicating for the 4 and 6 fermion interactions? So if we set the mass to 0, what we will see is that the 4 fermion interactions beta function simply looks like this, okay? And we recognize that the 0 of this prefactor is exactly the well-known Gross-Neveu fixed point for the 4 fermion interactions, which we've seen before. But there's now one interesting novelty which arises, which is that if we set lambda 2 to its fixed point value, then this renders the 6 fermion interaction exactly marginal. This is rather unexpected. Remember, this is a coupling which is a large anomalous or canonical dimension, okay? And now the 4 fermion interaction, okay, its fixed point is exactly the required input to make this coupling marginal. Now, we did all sorts of checks with this. In particular, we established that all of this is scheme independent, so there's no scheme dependence, that it does happen for any scheme you use. Okay, so it is hardwired into the theory. So if you make a plot of this, yes, so I show you now the analog boost plot of what we've seen a minute ago for the scalar theory. So we have a 4 fermion interaction here, the 6 fermion interaction there. This chiral line is what people have been observed previously, but what now happens is that the exactly marginal 6 fermion interaction is opening up a line of fixed points, okay? And this UV line of fixed points also has a finite range, and moreover, we do observe an endpoint, and this endpoint, surprisingly enough, has the exact same features as the scalar BMB fixed point. So it is something like the fermionic analog of the BMB phenomenon. Okay, now last transparency, you can now convince yourself that these solutions exist for all fields by doing these kind of heat plot, okay?
So Tom, can you move to your conclusions, please?
Yes, I'm concluding now, okay? And you can also compute your scaling exponents and get a similar feature as we found a minute ago with the scalars. So this brings me to my conclusions. I hope I've given you an overview of conditions for weakly interacting fixed points in general 4D quantum field theories. Gauge fields and fermions fermions with recurvers are clearly key here. Now, as an outlook, of course, in 4D, what you would like to do next is to investigate which of these features do survive at strong coupling, okay? SUSY supersymmetry will be a very useful tool to have a glimpse into strong coupling phenomena here. But also it will be interesting to understand whether some of these things can be downlifted to 3D proper fixed points. Now in 3D, I've explained to you interacting fixed points at strong coupling, particularly in fermionic theories. I've shown you some new results in the context of the 3D gauge Gross-Neveu models, which include fermionic BMB and okay, and here the outlook, of course, will be also to look into what supersymmetry is going to do and whether other tensorial structures in the fermionic sector can modify the results, whether we can switch on gauge fields without everything breaking together, but that's left for the future. Thank you very much for your attention.
Okay, thanks, Daniel, for a comprehensive talk, and just let's do the usual applause. Okay, so Simon Catterall's raised his hand here for a question, so go ahead, Simon.
Oh, hi, Daniel. Thanks for a very nice talk, very interesting talk. I just have a dumb question. What's the interpretation of a fixed point with spontaneously broken scale symmetry?
Well, yeah, that's a very good question. So it's a fixed point where, however, your potential has a technical singularity, and because of that technical singularity, the mass, which otherwise would be set to 0, so the gap equation which determines the mass,
right,
and which normally predicts the mass to be 0, this gap equation, due to, say, a singularity in your potential, now no longer dictates the mass to be 0. And so therefore, the scale symmetry is dynamically broken in these type of settings.
So if I was doing this on the lattice, I would find the correlation length didn't go to infinity. Is that the physical correlate of that?
I don't know how you would see it on the lattice, to be honest. Okay, but in these models with pen and paper, you see that very clearly because you get a rigorous, say, gap equation for the mass, and you realize that that has a prefactor which suddenly becomes 0, so the mass no longer needs to be 0.
Sounds like maybe it could be a first order phase transition and ending that line, maybe. Yeah. I don't know. Then I wouldn't technically call it a fixed point then ordinarily. It's not a.
It is a rigorous fixed point of the RG setup. It is a rigorous fixed point, okay, but it is true that in the phase diagram you also have further lines which I haven't shown or explained, which relate precisely to first order phase transitions.
Okay.
So this is really the physics of the, say, Bardeen-Moshe-Bender phenomenon, which in the 80s by François David and Bardeen and Moshe and Bender and co-authors has been investigated. Okay.
Yeah,
and
I was ignorant of it, I guess, and I was surprised by that. Not particularly by what you were saying about it, but the fact that it existed at all.
So back in the days, people were speculating that perhaps some of that could be of interest for 4D theories, because this could be, you know, yet another mechanism for mass generation. But
right.
But that hope never has materialized, to, in all fairness. Okay.
Thanks. Yeah.
Okay, so Simon Hans, you were next.
Oh, thank you. Thank you, Daniel. That was a lovely talk. I have a question about the Gross-Neveu model and the marginal nature of the 6 fermion interaction that you talked about at the end. I got the impression, looking at the results, that was obtained in the large N limit, and I wondered, you know, have you thought about the stability under 1/n corrections?
Oh yes, absolutely. No. State of affairs is this. As far as I can see, I believe this is a feature strictly valid at infinite n. It has some similarity to what we see in the scalar BMB, okay, where people have been trying recently to make this phenomenon survive at finite n. So the answer is not absolutely settled for now, okay, but at least in the point is this: infinite n, the theory is simply solved rigorously and exactly. Finite n, I have to do some approximations. If I do these approximations, I do not see that feature survives, okay? But what I do not yet know is whether this is my ignorance of doing the proper approximations, or whether this is strictly true in the full theory.
I mean, I just wonder if that's where the analogy between the scalar field theory might break down a little bit, because in the scalar field theory, n is part of the symmetry you're breaking, whereas in the Gross-Neveu model, it's not. I don't know.
Yeah.
Maybe we should move on to the next question. I think Lucas was next.
So I actually have a related question, and you have partly answered that already. It's related to the flow of lambda 1, I think you called it, in this Gross-Neveu plus theory. So this really looks like a one loop property. I mean, assuming that you would do some loop expansion and you would include some higher loop orders, would this property still hold, or is there any argument that lambda 1 equals 0 would be a fixed point of the argument?
Yeah, very good point. What I can say about this is this equation here is exact. It's not a one
at large n.
Yes, at large n. At finite n, say if you do LPA, there will be additional terms, but the feature that lambda 1 is a rigorous fixed point remains.
Okay, but that's so again a one loop. That's one loop argument now.
This is now LPA argument. Okay, at finite n, it's an LPA argument. Okay, so then LPA generates further terms, which are suppressed by 1/nf, but they will be there. Okay, at least in LPA, we do observe that mass equals 0 is still a fixed point. But then, of course, you can object that. Of course, we need to take more operators, higher, derivative operators into account. But that study we haven't yet done.
Okay. Okay. Thanks.
Just before we move on, Dan, that lambda 4, is that a typo or is that something else? On that slide,
Where?
in the beta 3.
Oh, yes, correct. Very good. Thanks for spotting. Okay, so this is the 8 fermion interaction. We just, I mean,
Okay.
I just wrote down the entire hierarchy of these equations, so that would be the 8 fermion interaction. Okay,
That's
so
right. I thought maybe it was that. At some point in the gather time, I want to talk to you about this privately. But move on to Reinhard was the next for a question.
Yes, thanks for the very nice talk, Daniel. And in order to motivate my question, some time ago, some people, including me, were interested in Lambo-Jonah-Larsenio models with 3 flavors and the Toff determinant, which did break axial U1 explicitly, but not the axial SUN symmetry. Yeah? So means, of course, if you have psi pop psi to the power 3 and several fermions, you have many different possibilities to write this term. But you did only, so to say, investigate one of these many possibilities, right?
yes, absolutely true. We had to start somewhere. We decided we take Gross-Neveu. As I mentioned, I mean, it's certainly interesting, of course, to to widen things up and look into all the tensor structures to understand.
Because as I said, exactly that version where it's a maximal monomial, say a determinant in the fields might be interesting because it keeps certain symmetries intact and also violates some subsets. So in this case, I mentioned axial U1 was explicitly broken, but not the axial SUN symmetry. Yeah? So, and this respect would be interesting to see whether your result is robust under such changes. Okay, that was only a question remark. Thanks.
Okay, and then just last question from Vieri, and then we'll move to gather time.
Yes, just a quick question. I think in the paper by Gaveschi and Copiani, you mentioned there is a small parameter, which is some sort of anomalous dimension one puts by hand. So I was wondering if you have some small parameters in your analysis, or you believe that there is no need. I think in the mathematical results, one needs some small parameter to control that.
Very good point. Thanks for reminding me of that. I did not mention that. So if you want to think in terms of a small parameter, in fact, it is the anomalous dimension, which is that small parameter. Okay. So definitely in these scalar theories, we know that at that large n fixed point, their anomalous dimension vanishes. Okay, which is why these equations can ultimately be solved exactly. Okay, and it so turns out that in the Gross-Neveu, say in the fermionic version of this type of theory, okay, at this fixed point, the anomalous dimension of the fermions also goes to 0. And that, if you want, you can use that in some sense, of course, as a small control parameter for your studies. The way which, see, in this RG type philosophy, okay, so what is important for us is, say, you start with this equation, and solving this in closed form is a nightmare. But if we make a large n, then you can guarantee that, where have I written it down? Okay, sorry, I'm looking for, I'm not finding it now, but say that the action we start with, which is just the standard kinetic term, but the general potential, that this is a closed set of equations. So this functional RG equation is rigorously solved, okay? And this comes about simply because at large n, higher derivative operators can no longer be generated if they are not already part of the initial action. So that's how that works technically, so to speak, in this formalism. Okay, it does entail that in this case that the anomalous dimension is 0. So it does also explain why this is linked to actually a small parameter. Does that answer your question?
Okay, thanks, Daniel.